it will be impossible to prove Blunder's theorem with what we are given, because we are given 3 wattmeters in the 3 lines. And we know Blunder's theorem is to determine only 2 wattmeters reading, either A and C, or B and C, or B and A. 2 wattmeter readings on the on 2 lines must be equal to the total power in the load, PA, BBC, and PCA. That is what Blunder's theorem says. That is only 2 lines with wattmeters on it. The sum of it must be equal to the total power. But in this instance, we are using 3 wattmeter method, which does not really go well. It does not really give us a basis for proving Blunder's theorem. So let's just try to find the total power dissipated in the load. I will just give us the basic technicality so that we can go through it. We are to calculate the active power dissipated in each impedance load. Each impedance load, we need to calculate this. And to be able to calculate this, too, you need to know the current that is going through each of the phase, the impedance, then you know the power in each of them. So to be able to determine the power, first let's go and quickly draw the phasor diagram. In the phasor diagram, we are given the source as a phase EC, which is the phase voltage 339.411 cos omega t minus pi over 1.8. That is the phase space. So you divide this by root 2 to give you the RMS value, which gives you 240. And the angle will be, because this is cos, you find this and you add 90 to it. So when you find pi over 1.8, it gives you 100, which means this is minus 100. Minus 100 plus 90 gives you minus 10 degrees. So that is the phase voltage, which is the reference. So it's at minus 10 degrees. So where is minus 10 degrees? This is minus, let's put our minus 10 degrees to be here. Let's say our EC is at minus 10 degrees here. Right? Then because it is positive phase sequence, line leads. So that means line leads by 30 degrees. So here will be ECA at angle 20 degrees. Then we can then find what is our next voltages. EAB, ABC, because it's a positive phase sequence. So this will be at angle what? 140 degrees. And this will be at angle what? It will fall in minus 100 degrees. So from there, you can now start to solve the problem. So the very first thing, we want to know the power dissipated here. The power dissipated here is with PAB, which will be VAB IAB cos VAB IAB. Our IAB is equal to what? VAB over ZAB. What is our VAB? Our VAB is at angle minus 100. And what is the voltage given? Phase voltage. So that means VAB is 9 is line. So we have to multiply the phase voltage by root 3. Then at angle minus 100 degrees divided by the ZAB that is given. That will give us our IAB, which is calculated to be 16.23 at angle minus 16.34 degrees amps. That's our IAB. So we need to find our IBC also. So once you find the IAB, of course, you can then find your PAB. our PAB, our VAB is what? Is 240 times root 3 at angle, then multiply by the IAB, which is 16.23, cos of the angle of VAB, which is minus 100 degree, minus angle of the current, minus 16.34 degrees. So that gives us our PAB. So we use the same thing to solve for the power in phase C, in that load, in this load for the phase C, BC, right? That means our PBC also should be what? VBC, IBC, cos VBC, IBC. So what is our IBC? Our IBC will be VBC divided by ZBC. What is our VBC? Our VBC is at angle minus 40. Don't forget that the voltage given is 240, so we have to multiply by root 3 to give us VBC, which is line 240, right, at angle 140 degrees divided by whatever our ZBC that is given to us is. So our IBC, when calculated, you get 14.134 at angle 85.31 degrees amps. So with that one, now you can now find what is your VBC is. Our VBC as our PBC then will be what? VBC, which is root 3 240, right, times the IBC. Our IBC is given as what? 14.134, right? Cos of the angle. What is the angle of VBC? Is minus 100 degrees, minus angle of IBC, 85.31 degrees. So that gives us the power dissipated here. And you do the same thing for the load in CA, which will be PCA, VCA, ICA, cos VCA, ICA. What's our ICA? Let's find our ICA. Our ICA is VCA over ZCA. So what's our VCA? Our VCA is at angle 20. That's root 3 times 240 at angle 20 degrees divided by our ZCA. So that gives you your ICA. Our ICA is given as what? 23.348 at angle minus 31.84 degrees amps. So after getting your ICA, you can now get your PCA, which is VCA, which is root 3 times 240 at angle 20 degrees. Of course, okay, we need to put the magnitude together, sorry. 240 times the ICA, which is what? 23.348, then cos of the angle of the voltage is what? Which is 20 degrees, minus ICA, 31.84 degrees. So that will give you your PCA. And with that, you can, if you have to find the total power that's consumed by the load, you can add PAB, PBC, and PCA together, and that sorts it. So let us assume you want to find even the total power consumed that is drawn by the line, which is using the wattmeter reading. Of course, you can find WA which will be VAB IA cos VAB IA. So where your IA will be equal to, you find your IA from here, which will be IAB minus ICA. Of course, you have your IBA, you have your ICA, you find your IA. Then you do the same thing, you find your WA. But this time around, because it is, you can see that the voltage there, because when you find your VAB here, you don't forget that your VAB is a line. So that means, and you are given phase voltage, that means you have to multiply by √3 to give you line 240 in this instance. But now, because of what we have here, the reason I say this cannot work out in that fashion is, let's say you want to find VAB as it is here, you know you will have you have to divide by √3. That means whatever you have to convert it to phase, which eventually still come back to the phase voltage, because because it is connected in phase, it's connected in staff connect form. So that means plus or minus 30 degrees will be the angle you had, or subtract angle based on the direction of rotation. Because it is positive phase rotation, whatever angle you have there, you subtract 30 from it. But this voltage here should be divided by √3 because of this phase. But unfortunately, here you have a phase voltage given for the question. Then your VAB, you have line voltage here. Line voltage, if you have to divide it by √3 as we have it, we are still coming back to 240, right? Then times IA. But in essence, what I've tried to tell you is that you cannot solve this problem. You cannot use this to solve blunders. Just solve, for the purpose of this, just solve. If you want to determine the wattmeter reading in all the three, you just have to find it in this form, then cos whatever angle between VAB, which is minus 100 degree, minus the angle of the current that you have, right? Then whatever the angle of the current that you have after, which is for the IA, which is minus, let's say our IA is minus 170.93 degrees, right? You still have again to now subtract 30 away from it. You still have to subtract 30 from that again. You understand what I'm saying now? That means minus 30 degrees again, because of the positive sequence rotation that you have there. That will help you. So the same thing if you want to solve for WB. WB also will be what? VBC divided by √3 IB cos VBC IB. Do you understand what I'm saying now? So with that now, that is the normal formula. But you remember that your VBC is supposed to be 240 times √3. Then if you have to divide again by √3, it comes back to the phase. That means it still comes back to 240 degrees. You understand? 240 volts. So when you have a 240 volt, you now multiply by your IB. Your IB that you are going to find from here, which is equal to IBC minus IAB. After getting that one, you now find the angle, which is also the angle of VBC. Your VBC is 140 minus the angle of the current that you find, IB that you find. Then you now subtract 30 degrees again from it. That will give you that the final phase difference that you have here. Then you sort it out, you find BB, then you do the same thing.